In this video, we will discuss how to find inverse of a quadratic function. We'll take a quadratic function in a standard form and then use completing the squares method to write it in the vertex form and then sketch the parabola and then find the inverse. So the steps involved will be first completing the squares. So this will also be a review for you to see how to do completing the squares. And then we'll sketch parabola. We'll use the step method. I hope you remember the step method. In a parabola, the steps are 1, 3, 5, 7 and so on, right? Times A, where A is the vertical stretch. And then, inverse of a quadratic function is not a function, because when you do the inverse, you get plus minus square root. That plus minus gives you two terms, right? For every input, therefore, is not a function. So what we can do is, we can restrict the domain to ensure that we are dealing with only one half of the parabola. In that case, the inverse of that half will be a function. So we'll also see the technique to restrict domain to ensure that the inverse function is also a function. And then finally, we'll determine the inverse of this function. To start with, let me take the quadratic function in standard form. Let's say fx is equal to 3x squared plus 6x minus 2. Now this is given in standard form. It's very difficult to sketch the parabola from here. One way, of course, is plug in different values of x, get y values and graph. Well, completing the squares gives us the parabola in vertex form, and then it becomes simpler for us to sketch. So let's follow the steps. First step is to factor out the leading coefficient. So when we factor out the leading coefficient, we get plus 6 divided by 3 is 2x. And we'll leave this term outside. Let me write it far away. Now, to make perfect square, the third term should be square of half the middle term, right? So, what is the half of 2? Half of 2 is 1. And so we'll just we'll add and subtract 1 square. Now you can see these three terms form a perfect square. This is x squared, and this is 2 times x and 1, 2x, and this is 1 square. So we can write this as x plus 1 whole square minus 1 minus 2. Let's open the bracket. 3 times x plus 1 whole square minus 3 times minus 1 minus 3 minus 2, which will give us minus 5. Now, this is the equation of our function in vertex form. Here, what is the vertex? Vertex is minus 1, 5. Now, this is a parabola which is stretched by a factor of 3. Therefore, if you want to sketch the parabola, the steps will be 3 times the standard value of 1357 and so on. Okay. What we can do is we can write down our values here and then sketch them on the graph. So from here, let's go with the center value vertex, then we'll move right and left and get all of the values. So center value vertex here is minus 1, 5. Sorry, minus 5, minus 5. So it's minus 1. It's always negative of this and this number as such, minus 5. Now, as I move 1 unit to the right, my next point will move up by 3 times 1, 3 units. So if you move right, then the value of x will be increased by 1. Minus 1 plus 1 is 0. And the value of y, as you can see from here, is increased by 3 times 1, 3. So minus 5 plus 3 gives us minus 2. Now let's move 1 more unit to the right. If we do so, in that case, plus 1 to 0 will be 1. And this time we are going to add 3 times 3 is 9. 9 to this. 9 minus 2 is 7. Now let's look into the terms on the other side. These are the symmetric terms. This is our line of axis, okay? Because that's the vertex, correct? So here, as we move left on the x-axis, we'll add minus 1 to this, right? So minus 1, when you add to this, it becomes minus 2. And to the y value, we'll add 3 times 1, which is minus 5 plus 3. We'll get minus 2. Let's move one more step on this side. So x value will be minus 3. And the y value will be 9 plus 3 times 3, 9 plus this, which is 7. And so on. This side also. Okay? Remember, this is our vertex. And this is the first step going up, correct? Now, let's try to sketch this on the graph. Okay? Now, the first point on the vertex was minus 1, minus 5. So let's go to minus 1, 1, 2, 3, 4, 5. The second point is 0, minus 2. 0, minus 2. You can see the steps are, first step 3, 1, 2, 3. Second step, we can take second step of 9, 3 times 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. And so on, the parabola will move. From the symmetry, we can draw straight away. So first step on the left, so let me write here. Our function which we are drawing here is 3 times 1, 3, 5, like this. So from the vertex, 1 step left and 3 up. 1, 2, 3. So that's the second point. Another step left, 9 up. 1, 2, 3, 4, 5, 6, 7, 8, 9. As you can see from the graph, our points are symmetrical, and that's a line of axis. Do you see that? Yes, that's how the parabola should have been. Okay, so let's join this. While I am joining these points, I will join one side with one color and the other side with a different color. So let me use green for this. And red for this side. Okay. Now to find the inverse of this function, we can do it graphically also. How? We can reflect this graph on y equals to x and get our points. So let me draw first line y equals to x. This is our line y equals to x. So if we reflect it on this. See, I'm also using this technique of showing you how to find inverse or how to plot inverse from the graph. Okay. Now, how to reflect it on this line? Let's go diagonally. This point reflection will be at, let's go diagonally, 1, 2 units. So its image will be at 1, 2 units. That's the image of this point. Now this point is invariant. It is on the line. Okay. Now this point, 1 unit, 1 unit. Now this point, the line is on this side. So it will come like this. 1, 2, 3. Diagonally move 3 units. 1, 2, 3. There we go. That's how it is. So this red line has been reflected to these points. Let me draw with a dotted line. You see that? So this is inverse of this half. Do you see that? Now we will similarly do inverse of the other half. This point will remain on the graph itself since it is invariant, -2, -2. And as far as this point is concerned, let's reflect it on this. So we come diagonally 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There it goes. So this half of the graph has got these points. Invariant point, this point, and here. So I'm going to join the inverse of green line with the dotted green line. Here it is. Okay. Now as such, the parabola which we have here is, this is fx equals to 3 times x plus 1 square minus 5. And that's my inverse function. Okay. This is my f inverse x. We'll determine the value of f inverse x just now in few seconds. Okay. Now let's check our points using the ordinate pairs. Okay. So if we see inverse of this function points as a set of ordinate pairs, the ordered pairs, then they should flip, right? So this point should be -5, -1. Then we have -2, 0. And then we have 7 and 1. So on. On this side, this is invariant, -2, -2. And this will become 7, -3. Correct? So these are our points on the inverse of a function. Okay, we just checked the vertexes. Here, the vertex is -1, -5. So let me write that in black. -1, -5. And we see that the vertex gets reflected, and this point is 1, 2, 3, 4, -5, -1. You see, by reflection we got the same result as we got from the ordinate pair. Similarly, you can check all other points. They will all match. Now, let's go ahead and see how to restrict the domain of our parabola so that the inverse is a function. As you can see, this is our parabola. It gets reflected on y over x, y equals to x, and we get the dashed line as inverse of a function. But this inverse is not a function at present, okay? Because it fails the vertical line test. If I draw a vertical line here somewhere, anywhere, except for this vertex, then we'll get 2 points. So for any value of x, we have 2 different points, right? So this is not a function. What we can do is we can restrict the domain of our functions so that its inverse becomes a function. Now, best way to restrict the domain is to start with the vertex. Okay. So what we will do is, let's take the values only for x greater than or equal to minus 1. So here the x value is minus 1. If we consider the domain of our main function only for x greater than or equal to minus 1, then we are considering the red line shown graph for our function, okay, whose inverse is this dotted line. Now, since we don't have the other half, this inverse is a function, correct? We have avoided the failure because now, see, earlier when there was a horizontal line like this, it will cut at 2 points. Now, if we consider only one part of the graph, this horizontal line test will not fail, right? If we could have taken x less than minus 1, in that case, we could have considered only the left half of our parabola. And then the inverse would have been this one. Do you agree? And that is again a function. So you could use any one of these. So you can see how we can restrict our parabola, the domain of parabola, so that we get inverse, which is a function. Right. Now here I will show you how to find the inverse of a function algebraically. Okay, we'll start with our equation fx equals to 3 times x plus 1 whole square minus 1. To do inverse, follow the steps. First step, replace fx with y. Okay, so y equals to 3 times x plus 1 whole square minus 5. So we wrote, instead of fx, we wrote y. Okay. The second is swap. Swap x and y. So we'll interchange. So instead of y, we'll write x. And instead of x, we'll write y. And then solve for y. So bring 5 here. X plus 5 equals to 3 times y plus 1 square. Now divide by 3. It becomes 1/3 of x plus 5 equals to y plus 1 whole square. Square root. When you do square root, don't forget to do plus and minus. So you write plus and minus. 1/3 x plus 5 equals to y plus 1. Now what is y? Y equals to 1 on this side, minus 1 plus minus square root of 1/3 x plus 5 square. Now write it in function notation. That means we'll replace y with fx. F of inverse x. Okay, f inverse of x. So this is written as f inverse of x is equal to minus 1 plus and minus 1/3 x plus 5 square. Perfect. Now, from the equation, you can see there are two parts to it, right? Now here, the plus and minus part. The plus part is shown by the line in red dots. So this, I could write this as f inverse of x equals to minus 1 plus minus square root of 1/3 x plus 5. Now because we are considering only the top part, we will not write like minus. We will use plus here and we will write negative for the f inverse of x minus 1 minus 1/3 x plus 5. You see that? So these are two different halves. We are considering restriction of domain. So if we restrict it to x greater than or equal to minus 1, then our answer is this. If we restrict to x less than minus 1, then our answer is this. But if we don't, then we should write f inverse and we should not write x. Do you understand? So we write f inverse of a, it becomes a relation, okay? So it's no more a function because of this. So we'll just restrict ourselves by writing f inverse of this. You can check your results. How? You understand This is a transformation of a square root function, right? Now, for a square root function, it starts like this. Minus 1. Minus 1 indicates that the graph moves 1 unit downwards. And here in the bracket, plus 5 indicates that the graph moves 5 units to the left. So basically the vertex moves 5 units left, that means minus 5, and 1 unit down. So this point actually comes to this place, and that point happens to be minus 5, minus 1, which exactly we have here, right? So that shows that all our results are in unison and they are showing us exactly the same things, correct? So with this example, I hope you had a recap on how to do completing the squares. So we showed you completing the squares method. In completing the squares, whatever equation is given in standard form for a quadratic function, you have to factor the leading coefficient from the first two terms and then take half of the coefficient of x, square it, add and subtract the same term. When we are adding and subtracting, here in this case 1 and minus 1, it is 0. So same thing, it's an equivalent equation. But that helps us to make a perfect square. The first three terms here are perfect squares. X squared plus 2x plus 1 can be written as x plus 1 whole square. If you expand it, you will get this function, x squared plus 2 times ab, x and 1, 2x plus 1 squared. And then minus 1 squared is minus 1. That was our constant. Now you open the brackets, multiply 3 with this and then with this. That's the distributive law. Once you do that, then combine the like terms. Here the constants, which is minus 3 and minus 2, will give you minus 5. The vertex here is this. Axis of symmetry is x equals to minus 1. On the axis of symmetry, you have the vertex with the value minus 1, minus 5. Now, since a is our stretch factor, therefore the graph, it is positive, right? So the graph moves up with a stretch factor of 3. So it's like plus 3, right? Moving up. 3 times 1, 3. 3 times 3 is 9. So the steps are 3, 9, like multiples of 3. 4, 1, 3, 5, 7. The vertex is here. We just plotted some points for convenience. And then translated those points on our graph, correct? And in the graph, you can see I purposely have drawn one half of the graph in red, the other half in green, just to show you it's a parabola, and once it gets reflected on y equals to x, we get inverse of this parabola, which is a square root function, okay? But since it fails the vertical line test, it is not really a function. So it's just, we can just write it f inverse of a relation, not as a function, okay? But here what we did was, we learned another technique to ensure that the inverse of our function should be a function. Our function was not, inverse of our function was not a function because it failed horizontal line test. Now by restricting the domain, we avoided it. We took only one half of the parabola. So you could take either for x greater than or equal to this or x less than minus 1, the axis of symmetry. See, this was the axis of symmetry, correct? This side or that side. In either case, the inverse of a function is also split into two halves, thereby the vertical line test is passed. So if you consider only one half of it, then for the red, you get the red dotted line, and for the green dotted line shows you the inverse of a function. Algebraically, inverse of the function is calculated following the standard steps. Replace fx with y, swap x and y, and then solve for y, correct? Remember, whenever you are doing square root from square, then take plus and minus sign. So we got a function, inverse of the function, which of course is not a function since we have two values. See, two values. Because of our restriction, we manage to get inverse two different inverses, both as functions. Okay? I hope you appreciate the method, and it will help you to understand how to find inverse of quadratic function. Thank you.